Welcome to Cryptography on Hardware. We have up to now seen different public key cryptographic algorithms and also how to implement different kinds of adders, which are essential for most of the public key crypto algorithms. And as we learned, some of these algorithms actually need also multiplication. And this addition or adder we need for the multiplication or for multiplier. And most of these algorithms actually use modular multiplication, and also the RSA and Diffie-Hellman, they need modular exponentiation. And then today we see how we can implement multiplication in an efficient way. Yeah, you may say that, okay, multiplication easy, I just ask the synthesizer to do it for me. That's true, you can do it, but of course for short operands. Yeah, I mean, if you want to, for example, implement RSA with 2048 bits, and then you want to have the parallel multiplier, just ask the synthesizer to implement multiplication for you or multiplier. This will not be that easy. Schoolbook multiplication is, I guess you should be able to easily implement this. You have n bit A and n bit B, and then you want to implement the just multiplication between A and B. At the moment, no modular multiplication. Yeah? And then what you do, easy, you take the first bit of B, LSB, and then multiply it by all bits of A. You just write it B0, A0, B0, A1, B0, A2 till B0, n minus 1. And then you take the second bit of the B and you do the same, but you shift the result actually one bit to the left. Yeah? And you continue this till you have implemented or multiplied the last bit or MSB of B to all bits of A, and then write them down like this, that for every row you are shifted, or you shift everything one bit to the left, and then you sum up. Yeah, means that you should add the values here. Yeah, I mean, then this is the reason that you need the adder or addition. And the result actually has two n minus 1 bits, but because we add all things together, there might be a carry here, and then in total you have 2n bits. Means that each operand has n bits, and then the result has 2n bits. Yeah? This is something that you can easily implement. Now, let's see if you implement this in VHDL, parallel multiplier. Of course, you can do all of these things that I said. Just implement this bitwise and then add and so on. But you can easily ask the synthesizer to do it for you. You have fully combinational circuit, A, B, each one n bit, of course, the parametric, and the output R is 2n minus 1 bits. And then what you do, you define something as unsigned values, the signals. And then you just easily say the value of A or unsigned value is here unsigned of A, unsigned of B, and then easily multiply. And then at the end, you convert it to a standard logic vector. That's all. Easy. We know that this is pretty large. Yeah, we know how many adders you need if you want to implement the adder at every stage. Of course, I mean, you don't need the adder every stage because some values are actually 0 here. But if you want to implement this in a schoolbook way, then you need n times the adder, or n minus times one adder, and each stage of the adder at least needs 2 n-bit values. Yeah. Or in some cases, n plus 1 bits. There is a more optimum way, which is called parallel array multiplier, and this example is just for 4-bit by 4-bit, means that n equals 4 from 0 to 3. And here is the first module, is that they receive all bits of A and all bits of B and generate something called Pij. And the Pij is just a multiplication or AND between every possible bits of A with every possible bits of B. Means that Pij is AI multiplied by Bj. Multiply is the AND, if you have just single bit. Then when we have 4-bit by 4-bit, then 16 different Pij we have. This is actually similar to here. You have exactly n by n or 2 to the or n to the 2 different Pij. Now, how it's implemented, you see P00 directly comes here. I mean, if we look at here, the all values are 0, then this directly comes here. And the next one, yeah, if you have a full adder, and we can have also half adder, but the full adder you have, here you see the carry is 0, and then 1, 0, and 0, 1 are given to the full adder, and then you get the result. And 1, 1, and 2, 0, 0, 2 are given here, and 2, 0 should be also added to this. Anyway, with some intelligent way, you can instantiate just 3 full adders every row, and then in 4 rows, then you will have the output, which is the multiplier or multiplication of 4-bit by 4-bit. Then for that, there is a Wallace tree, which makes Pij, as we discussed. You know, this is the same way. And then it assigns a weight to each Pij. Yeah, as a weight is just actually 2 to the I plus j. And then it adds all Pij with the same weight. And then it will be something like this. Here in this example, again, 4 by 4-bit multiplier. And these are the Pijs that you see. You know, it means that 0, 0, and 0, 1, and 1, 0, I mean, they have the same weight. Then they are in the same here layer. 0, 2, 2, 0, and 1, 1 have the same layer. 0, 3, 1, 2, 2, 1, 3, 0, they have the same layer, and so on. Now, and then it actually is somehow similar, but you see here that these two guys are going to the half adder, and then the carry of this, carry of every part, actually goes to the next layer. Yeah? Means that the carry of this goes to the next layer, and then you have here, in this case, you have 0, 2, 1, 1, and 2, 0 here, 0, 2, 2, 0, and 1, 1, and the carry coming from the last stage. And it provides also 2 carries. And these 2 carries also go here, means that 0, 3, 1, 2, 2, 1, and 3, 0, and 2 other carries coming from the previous stage should be added together, and you see it generates 3 carries, yeah, and so on and so on. Yeah. Of course, this is scalable, but it's not necessarily simple. Yeah, sometimes you need to sit down and make it in a more optimum way. Yeah, again, similar to the previous one. You see we had 4 stages of the full adder. Here, you see there are at most 3 stages. Good, as I said, but you can ask the synthesizer to do its job, and of course it has some algorithms and some templates for the multipliers. N-bit multiplication in 1 clock cycle is a parallel adder. It's very slow and very large. I mean, slow not with respect to the number of clock cycles, with respect to the critical path delay. How fast can be the clock? And then alternatives are serial multiplier and also serial parallel multipliers. What is a serial multiplier? Now, it's super simple. You see, I have A and B as just 2 registers. I mean, the value that I have, they are stored in the register. And then in every clock cycle, I just have the result of 1 full adder. Means that I don't have a lot of adders, just a full adder, 1 single instance. And the result, of course, should be stored in the register. Yeah? And then 1 flip-flop to store the value, the carry of the full adder. Because look here, what I can do. Here. I can implement this too. I mean, add, perform the AND operation, and then I store this. And then what I want to do, I actually want to, let's say, make this row first. And then carry of, of course, the current result, the previous result should be added with this, and the carry of this should be added to this. Means that suppose that I'm here in the middle. Yeah? The 0, 0 ignores, I start from here, then suppose that I already made this and I added everything. Then I have a vector of intermediate value of the C up to this row, and then I take this and I add it to all the values that I have here that I already stored, and then the carry of this goes to the next addition that I have in this column, and so on, but only with one full adder, and for that I need to have a register to store the carry. How this works, this is the procedure. Here, as I said, there is a register and it's shifted. You can shift it to the right, and there is a B register which is shifted also to the right, and I have one AND operation here. And as I said, this construction is there, and then there is a here multiplexer which selects whether the output of the full adder is stored here or the output of the carry. Because when you add everything, the last bit should be also stored here in this register when there is nothing to add, and then the last carry should be stored in the register. In the first clock cycle, the reset is 1 and reset C is 1. What does it mean? Here, the output register should be completely cleared, and this flip-flop, which stores also the carry, should be cleared as well. And of course, at the same time, we load given input to A and B in parallel way. Then what we do in the next clock cycle, we keep B, which means that B0 is here, and then we shift A one bit to the right. And then the output of this actually goes to the full adder, and the output of this is there, and then we can already shift here. And then what we do, we also store the carry out to the flip-flop. Means that this is enabled, and we also shift here 1 bit to the right. And we repeat this n clock cycles, means that completely A is rotated n bits or n times, means that B0 is multiplied to all bits of A, and the result of the value which is in the register here will be bit by bit added to the output of this AND gate every clock cycle, including the carry. And one more clock cycle you need to shift to store the carry here. And this is that clock cycle. In this clock cycle, then we shift the 1 bit, we shift 4, which is here. We shift the 4 because we need to also shift 1 bit, the output register. And at this time, select C is 1, means that the output of the flip-flop should be taken to be stored here. And at the same time, we reset the flip-flop. And then we need to repeat this n times. Means that in total, we have n plus 1 multiplied by n clock cycles to implement this fully serial multiplier. Of course, one more clock cycle just for the reset. And I have this implementation for you as serial multiplier. May look a bit complicated because there are a lot of signals, but every of this signal that you have here, they should have a name. This is a loop, this is a loop, the output of the AND gate, the output of the full adder and flip-flop, and so on. There is a process, whether we do the reset or not, and when the reset is there, the inputs are stored in the register, and register R should be completely 0. This is here. This register R should be completely 0. And register C, which was storing the carry, should be also 0. And then we have a counter, of course, 2 counters we need. One for the internal counter, another one for the external counter. And here we have some states, what we need to do. Then here, if the reset is not 1, then of course we go to the next stage. The other process decides what the next state is. And then if the shift A should be done, then we rotate A or rotate B, and then we shift half. Means that here the R sometimes should be just shifted like this, sometimes should be shifted fully. And this is also done via this, that we fully shift including the carry, register carry, or we just shift part of this, because in the intermediate way, when we are in this loop, we need to shift this, but not every bit. Just n bits, n most significant bit should be shifted, not in this bit which is here should not be touched. And again, some other signals. If the controls reset is 1, then we reset the counters and so on. Now enable the counters and so on. And as I said, it may look complicated, but if you follow the states, you understand what you should do. You can have, instead of this serial multiplier, which is very slow, but it might be the smallest implementation, although it has some registers. You should not forget that it needs one register n bit for the input and another n bit register for another input, and two n register for the output, and the registers are not cheap. Then you have some registers, but it will be very slow. N plus 1 multiplied by n, I mean log, not log, but the complexity of n to the 2, at least it has. But now serial parallel multiplier means that you have some part of the implementation as serial, some other parts parallel. It means that you have an adder instead of a full adder. You have an implementation of the n-bit adder, like the Kogan-Stone adder or any kind of adder that you have that you can instantiate here. But then what you do, the A is fully there, and then with every bit of B, you decide what to do. I mean, B0 is multiplied fully by this, means that if B0 is 0, then of course everything is 0, then 0 actually goes here. You don't need to implement the AND. You can have just a multiplexer, and if B0 or the index of the, or the current index of the bit, current bit of the B is 1, then the A actually passes through this multiplexer. And then this goes to the adder with again n bit of the most significant part of the register. And then this is similar to the before, which was fully actually serial. Now the result of the adder has a carry, and then it will be n plus 1 bits. And this is stored exactly here. It means that, look here, I mean, it takes from n to 2, n minus 1, but then the output is stored from the n minus 1 to the 2, n minus 1. And then, of course, you need to shift. Means that in one clock cycle, you do reset. In the next clock cycle, you, of course, everything, as I said, is available here, combinational. But then this is rotated 1 bit, the B, but then 2 loads this part, means that n plus 1 bits are loaded here, but at the same time, you need to shift the rest of the values which are in the register, but from here, from this bit. It means that we should not ignore the n minus 1 bit. Then this is shifted here, and this should be repeated n clock cycles, and then you have in n plus 1 clock cycles, you have the output of the multiplier. Now, this is a combination between the serial and the parallel multiplier. This is another architecture of the serial parallel multiplier. That its example is just a few bits. You can see the ANDs are there. The AND is actually exactly that multiplier, the multiplexer or the AND gate for the B. Or here you see the indexes are x0, which will be multiplied by all of the bits of y. But here there are registers here. I mean, these delay elements are those registers per clock cycle. x0 is given to here, and it goes to some full adders. What you see here, they are also the adders, and the output is sum and the carry is stored in some registers. And then next clock cycle, everything is shifted, means that x1 is given here and x0 actually appears here, and the rest are 0, and that you provide the next output of the result of the multiplication. And then you continue this, 8 clock cycles, and then you are done. How many of this you need? Yeah, exactly based on the number of the operands. Yeah, the operand is here, example, 4 bits. You need 4 times of this and also 3 full adders with some registers. Now, this is a different way of implementing this, but the number of clock cycles is the same. Because 1 clock cycle, you need to first put here 0 in all of these registers or reset the registers. Good. Now, one thing which is important to know is that when the operands are super large, you know, for example, you have in RSA 2048 bits as the operand, then the multiplication is not that cheap, you know, either in hardware or software. But there is a scheme which is called Karatsuba multiplication or multiplier, which makes it easier and also can be used in a recursive way. What it does and what is the idea? The idea is that you have a small multiplier, but you want to implement a larger multiplier based on a smaller multiplier. Now, for example, you have 2048 as the bits of the operands, but then you divide it first by we will see, by Karatsuba multiplication into the multipliers with half size, means 1024 bits. And then again, divide this to the smaller one with 512, and even a smaller and a smaller. Particularly if you have a microcontroller, I mean, we are not implementing any software here, but if you have a microcontroller or microprocessor which has an instruction as the multiplication, for example, 32-bit by 32-bit multiplication, then you can divide this multiplication by Karatsuba multiplication up to, let's say, 32-bit, and then use the multiplier inside the microprocessor, which has a 32-bit by 32-bit, and then implement the larger multipliers. The Karatsuba says like this, that you have operands like A and B, and each one has n bits, and then you divide it into half bits, I mean n half bits, in a way that, okay, you can write A as a smaller A1 multiplied by T plus A0, and then this T is actually 2 to the n minus 1, 2 to the n by 2. Sorry, T is 2 to the n divided by 2. And then you can write it like this, means that you actually divide this. I mean, you don't perform any division, but you take n half bits from the left side to A0 and half bits of the right side to the A1, and the same for B. And then you just write the formula of the multiplication. You say, I have A multiplied by B, I can write all of this. Yeah, A1t plus A0 multiplied by B1t plus B0, and then you end up with these terms that A0 is multiplied by B0, and there are two terms like A1 B0 and A0 B1 multiplied by T, and another one A1 B1 multiplied by T2. And you know that this is just shifting. You don't need to multiply it by T. Just shift half n bits, and here actually shift completely n bits. No? Then if you have a multiplier which works with half n bits, then you can use this module here. Now this actually is written like this, that this is called P3, this is called P2, and this guy is called P1. One more important thing is that P2 can be written a bit differently. Yeah? P2 was actually this guy, yeah? But you can write it differently. You can say actually A0 plus A1, yeah? A0 plus A1. The two parts of the A are summed together and then multiply with the sum of the B0 plus B1. And then minus what? Minus P1 and minus P3. Yeah, in this way. Yeah. Why is important? Because if you implement this, yeah, you need to have 1, 2, 3, and 4 multiplication. But if you write it like this, you will have just 1, 2, and 3 multiplication. But of course, you need addition here, you need addition here, subtraction, subtraction. Yeah, means that 2, or let's say 4 times, or 4 times you need to use the adder module, of course, I mean, because subtraction and adders are the same, yeah, with a single bit of control logic. But if multiplication takes very much time, then you can actually just reduce this to 3 multiplications. Now this is the scheme, just to show you where they should be added together if you sum them up. This is P3, the result of the A0 multiplied by B0, and this is P1, the result of P1 multiplied by B1. Yeah? Because this guy actually should be multiplied by tier T2, means that there is no intersection between them. Means exactly you can concatenate P0 and P3 together and say this is the n-bit word of the sum of P1 plus P3, and there is no carry at all. But then you need to position P2 in a correct location and then sum it up. Yeah? Means that you need to first calculate P2, and what is super important, the P2 actually can have carry. Yeah? Means that P2 is not necessarily n bits, it can be actually n plus 1 bits. If you get back here, see here, this is n bits, this is also n bits, and this can be n plus 1 bits because of the carry, and this is the same as here, yeah? Because you sum them up and sum them up here, and you subtract it from something here, which is not necessarily actually n bits, yeah? Can be n plus 1 bits. And then you need to position P2 in a correct location or position and then sum it up. Means that after that, you need just an adder, and then the adder should not take here the 0 because the output of this part is exactly 3. But definitely you need an adder to take n half bit of B3 and completely with P1 and then add from here to here. Yeah? And then if you don't have the this multiplier, then you need to again divide it, and again divide it, and again divide it. Yeah? You mean in a recursive way you can implement this. How the modular multiplication works, you know? I mean, we have seen the multiplier. I mean, this was a arithmetic multiplier without any modulo. But the modular multiplication is simple, of course, but you should keep in your mind that for every time that you perform an addition, you have to check whether this is larger than the modulo or not. Yeah? And then subtract it from the modulo if it's larger or equals the modulo. For example, here there is a flow chart that here again we have x and y as the inputs, and the xi is the bit of the x. And every time you decide whether actually y is coming here or 0 comes here, and then what you do, the result of the p, you know, which I mean, if you implement the multiplication, you multiply p by 2 or shift it. And then every time that you do this, keep in your mind that you have to check it 2 times. You know? You have to check it 2 times whether this is larger or equals modulo or not. Why? Because the result of p here, this can be already larger or equal the modulo, and then you add it also with something else. Alternatively, you can here implement p equals 2 by p, means that you multiply it by 2 and then check once here, and then add actually the result of this y and then check after that one more time. You know? I mean, it doesn't have any effect. I mean, either you do it before this and one of them before this end, or both of them after this end. Before showing you the exponentiation, we can see the implementations. This is a parallel serial multiplier. I mean, in the same way with the same ports. And you can also simulate this and see how many clock cycles actually it takes and how this works. These are actually the same thing. Yeah, when the reset we load, if we are not in the reset, we check and we go to the state. And this is exactly what I have explained, that we have a counter. And what is important here, then we do, actually I wrote the adder in the serial parallel multiplier. We just ask the synthesizer to implement this. Yeah, I mean, instead of instantiating any adder. Or of course, as I said, this can be replaced by any adder module because it considers, of course, n plus 1 bits, and because the output should be n plus 1. Yeah. And then here it decides whether it should update or stop or something else. What else? Before looking at the exponentiation or modular exponentiation, I have here parallel serial multiplier module, but it's actually modular multiplier. Means that n is there and also there is m as modulo. And of course, I mean, it's not written here, yeah, but m should have also the same size as the n. Yeah, it's 4-bit, m should be exactly 4 bits, yeah, the modulo. And it performs the same thing as before because the serial parallel multiplier, but instead of this adder that I have explained, you see here I implement 2p, or 2 multiplication by 2 multiplied by p, and then also perform here or check whether this is larger than the modulo, and then again I perform here the addition, what we have seen in the slide, and then again check whether the output should be reduced or not. Yeah, and then the sum will be provided. Yeah. Then this is the serial parallel modular multiplication, and I use it actually in exponent or modular exponentiation. What is or how the modular exponentiation should work? Is nothing else than here square and multiply. This is what you have already learned, square and multiply. That you take the z, you multiply it by itself or s squared, and then you check the bits of the input. If it's 1, then you do the multiplication. What I have done here to reduce the area, but of course it's not very efficient in terms of the latency or the number of clock cycles, is that I have a module which is the multiplier, and then sometimes I give both inputs to the multiplier to implement the squaring, and sometimes I give another input to the multiplier to implement the multiplication with m. Yeah. Then how this works here. When the reset is 1, actually the z, the output, because it's the exponentiation, is just filled with everything 0 and then the LSB 1. Here it is, you know, z equals 1. And then the multiplier module has, of course, a start and a done signal. And it has a clock because it's a serial parallel multiplier. It can be also a fully parallel multiplier. And then there is a signal called the square, whether we should perform the square or multiplication. You see the square takes the m, the multiplication takes the m, the other operand. And if it's a square, then it takes both z. You see both z actually go to the multiplier module, and the output of the multiplication, again in a loop, will be stored in the z. And then in some clock cycles, you need to say, okay, the output is ready here, and store it in the register. And of course, for that, you need a control module. The control module has a reset similar to this. And then there is a d, which is the exponent, here based on the bits of the d, that we shift every clock cycle to the right. We decide what to do, and this control module provides the enable signal for the z, an enable signal for the D to shift, because we don't do it every clock cycle, and then define and controls also a square signal, whether we need to perform the square multiplication, and also start the multiplier module and wait till the done signal is 1. And this is fully made here. Again, we have N1 and N2. We have 2 sizes for the exponentiation because it should not be necessarily the same size. No? I mean, we perform what? We perform here M to the D, and the size of M and D should not be necessarily the same. There are 2 different sizes. You see here A is N1 bits and D is N2 bits, and the reset and the clock and the output, which will be also N bits, because you implement A to the D, and the modulo what? Modulo M, and this is the size of the N1. Yeah, and then, as I said, here the parallel serial multiplier, modular multiplier is instantiated, and again, the control logic exactly does what I have explained here. Is just about the registers and the counters and what should be the next state or the next to store the next state, and what to be stored in the registers. And here are just the control signals. And probably, if you look at it more carefully, and you will probably understand how this works. But this is the procedure is pretty simple. That every clock cycle, what you should do first. The enable signal should be 1, means after the reset, this should be stored, and then define, because here we are in the squaring. Then once we need to perform the squaring, then the square should be 1, and then start this, wait till the done signal is 1, and then when the done signal is 1, then enable here the Z register. At the same time, no, we don't shift here, but at the same time we take DI and decide what we do next clock cycle, whether we need to perform this or we jump. No, it means that we don't wait for the multiplication here. If this bit is 1, then again we say the square here, in this case 0, and then I start the multiplier again, and the rest works exactly similar to the other clock cycles or the rounds. And then after some clock cycles, of course, there are some overhead with respect to the starting and waiting for the done of the modular multiplier module. But of course, this time, if the modular multiplication module, for example, needs 100 clock cycles, then 100 clock cycle multiplied by n, you need to wait for the scoring, and 100 clock cycles multiplied by the number of bits of the D, which are 1, means that the Hamming weight of the D, you need to wait for the multiplication. And if you do it very carefully, you can save some time with respect to storing the register and shifting this guy, then the overhead is lower. Now, but this will not be very, very fast now, because anyway, bit by bit, you need to check for the square and multiplication. At the same time, you need to wait till the modular multiplication module actually did its job. No? For every of these implementations, I provided also a simulation or test bench for you. I mean, you can try and check it for yourself. For example, here, test exponent. And there are some tests here, and what should be the output, and so on. Then you can check change the parameter, and then run it by yourself and see how many clock cycles actually it takes.